All right, part 2 here of chapter 8. We've looked at these 3 techniques: use substitution, using the integral table, and then trig identities. Let's look at a couple other techniques. So again, just looking at some examples. This is example 4. This next one that we're going to do is the integral from 0 to pi over 4 dx over 1 minus sine x. Okay. Just going through the list that we have so far, we could not do u substitution here. If I let u be the denominator, I do not have the derivative of that. Nothing on that table matches to what we have here. And then there's no identity that we could use here that would really help us out. Usually if you just have cosine or sine, we can't really do much. It's only when you have cosine squares or sine squares that we can do something. But we can force this to be cosine squares or sine squared by doing something called multiplying by the conjugate. You probably saw conjugate stuff back when you were doing complex numbers, but it works for other algebraic techniques or topics as well. Anytime you have 1 plus or minus sine, or 1 plus or minus cosine, or cosine plus or minus 1, you can multiply by the conjugate. The conjugate is just this factor here, but changing the sign on the inside. So we're going to do the integral from 0 to pi over 4 of this dx over 1 minus sine x, but I'm going to multiply the top by 1 plus sine x, and I'm going to multiply the bottom by 1 plus sine x. We're really only multiplying by 1 here, but this way it kind of simplifies down, and let's see how that works. When I multiply the top by 1 plus sine x, there isn't really much that I can do, but just leave it as 1 plus sine x and then that dx. But when I multiply the bottom by 1 plus sine x, we're going to FOIL these things together. So we're going to multiply the 1's together. 1 times 1 is 1. My inner is going to be negative sine x times 1, which is negative sine x. My outer is going to be a positive sine x, so those two things just cancel out. But then I have a negative sine x and a positive sine x that will multiply together to be a negative sine squared. Now we're going to use the Pythagorean identity. The Pythagorean identity is cosine squared plus sine squared is equal to 1. But if I subtract the sine squared over to the other side, I get cosine squared is equal to this 1 minus sine squared. So when I do that substitution of that Pythagorean identity, I still have the 1 plus sine x there on top dx. But in my denominator, 1 minus sine squared, I'm going to replace with cosine squared. Okay, still looks kind of awful, I know. So now the trick is going to be, we have 2 terms up in the numerator and just a single term there in the denominator. So we're going to divide each of those terms by that cosine. So we still have the integral from 0 to pi over 4, but then I have 1 over cosine squared. 1 divided by cosine squared, I could rewrite using the reciprocal identity as secant squared. Plus, then we have sine over cosine squared. We're going to do some more identities here. I'm going to think about sine over cosine squared as sine over cosine and then a separate 1 over cosine. That 1 over cosine is just secant, and then sine over cosine is tangent. Again, use that trig identity. These look awful, but they have very nice antiderivatives. These should be ones that you remember back from Calc 1. Secant squared has antiderivative of tangent because the derivative of tangent is secant squared. Secant tangent has antiderivative of just secant because the derivative of secant is secant tangent. This is my antiderivative, and I just need to evaluate that from 0 to pi over 4. If I plug pi over 4 into this, tangent of pi over 4 is 1. You could look at a unit circle for that. Secant of pi over 4, you just have to do the reciprocal of cosine of pi over 4. Cosine of pi over 4 is root 2 over 2, which means that secant of pi over 4 is the reciprocal of root 2 over 2, which is just root 2. Minus plugging 0 in, tangent of 0 is 0, secant of 0 is 1. My 1's cancel out, and we just get the answer square root 2. So square root of 2 is going to be my answer here for the integral 0 to pi over 4 dx over 1 minus sine x. And the technique that we used here is multiplying by the conjugate. So I'm going to add that over to the techniques page. So technique 4, sometimes multiplying by the conjugate. Okay, great. Well, let's look at another example. So the next example that we're going to do is this one. This, I remember, was always everybody's favorite. That's sarcastic, by the way. I think everybody hated this one. So this would be the integral of 3x squared minus 7x all divided by 3x plus 2 dx. Okay, so for this one, again, u substitution would not be helpful here because we don't have a derivative anywhere. Some people would try to separate this out into two separate fractions, and that may work, but there's a better technique that we can do here. The technique that we would do is noticing that we have this rational function, this fraction here, where the numerator has either equal or bigger degree than the denominator. In that case, we can simplify this down by doing long division. And I can't stress enough, because nobody can seem to remember, but long division is when the numerator has equal or higher degree. So even if this was just an x up top, you would still do long division. All right, I'm sure it's been a while since you guys have done long division with polynomials here, so let's look at how to do it. That 3x plus 2, we're going to put out in front, and then we're going to divide that into 3x squared minus 7x. There's not a constant term here, so I'm going to add in what we call a ghost term, just to have a placeholder for the constant. Then you want to ask yourself, what do you have to multiply 3x by to get to 3x squared? It's just missing an x, so I'm going to throw it up top there. Then I'm going to multiply that x by the 3x plus 2. X times 3x is 3x squared, right? We planned that to happen. And then x times 2x, x times 2 is 2x. Whatever you need to do to remember that you are subtracting this whole thing away. So 3x squared minus 3x squared is just 0. But then we have negative 7x minus 2x, which is negative 9x. And I guess the 0 comes down. Then you just keep going. What do you have to multiply 3x by to get to negative 9x? It's missing a negative 3. Multiply that negative 3 by these two terms. Negative 3 and 3x is negative 9x. Negative 3 and positive 2 is negative 6. But again, you are subtracting this whole thing away. The 9x's cancel out, but then we have 0 minus negative 6, which is really positive 6. What that means is that this division, this quotient here, comes out to be the quotient x minus 3 plus the remainder 6 over the 3x plus 2. All right, so this term here is this, x minus 3 plus the 6 over 3x plus 2. And what that means is that integral, 3x squared minus 7x over 3x plus 2 dx, we could just rewrite as the integral of x minus 3 plus 6 over 3x plus 2. Okay, and then we can just do this. We're going to think about this as 3 separate integrals. The x is easy. The negative 3 is easy. This one would take a little bit of work, right? It would just be a u substitution, though. So here we're going to let u be the 3x plus 2, and then du would be 3 dx, which means that this I'm going to leave as the integral of x dx plus the integral of negative 3 dx plus this one I'm going to do the u substitution with. We still have that 6 up top, all divided by this 3x plus 2 is now going to be my u. But then the dx I'm going to substitute out as 1/3 du after you divide the 3 over here. The 6 and the 3 cancel out to be 2, and then we have this 1 over u. So then just doing the antiderivative of each of these, x is going to go to 1/2 x squared. Negative 3 is going to go to negative 3x. Be careful with this one because I don't think we've seen one like this in the class. The 6 and the 3 cancel out to be 2. And then 1 over u has antiderivative of the natural log of the absolute value of u. Do not forget to substitute out the u, though. You never want to leave a u substitution in your final answer. So we have the 1/2 x squared, the negative 3x plus the 2, and it's going to be the natural log of our substitution. Remember that u was 3x plus 2. You also have to have the absolute values. Don't forget to write those out. Okay, cool. So there's another technique here, and that other technique that we just saw, long division. Long division whenever the numerator's degree is the same or higher than the denominator's degree. I got 2 more examples that I want to look at here. One of them is pretty difficult, so I'm going to make sure to take my time with it. So I'm going to make one more video here for section 1.